All right, how's it going, everybody? We are here on Thursday of February 18th. We're going to talk about section 2.3 today, analytic methods for special systems. Um, Full title in there. So today is going to be, uh, I would refer to this as our sort of last regular day of chapter 2. Chapter 2 is pretty short. It's our concept chapter that's trying to set us up for chapter 3, where we're really going to look at our analytic techniques more broadly for systems. So what we're going to do today is look at the systems that we're already able to solve without learning any new techniques, right? So again, this is sort of us handling all of our business before we really truly start with our systems analytic methods in chapter 3 here. So today we get our special cases. And what you guys know is that I am sort of, rather than just like following through chapters 1 through 3 in the textbook, we're sort of going to take a little pause and cover all the numerical components of this class. We're going to do all of our saying, listen, there's things that we can't straight up solve. We still want to be able to figure out how do we get numerical approximations to solutions? How do we produce the graphs that are produced at our where we've been using technology to graph these phase planes? Where are they getting those pictures from? All that good stuff. So uh, this will sort of be our last regular video covering a section of the class for about 2 weeks. Next video and both videos next week are going to be covering programming topics. They're still covering regular sections from the textbook, as you can see right there. Section 1.4 is Euler's method for single ordinary differential equations. Section 2.4 is Euler's method for systems of differential equations. It turns out the programming for those is going to basically just be, we're going to copy and paste a bunch of the stuff in 1.4 so that there's two versions of it for 2.4, and then we're going to kind of keep on cruising right there. It's not going to be a huge step up, but we are going to look at some other special things that are out there. We're going to touch on a little bit of things that are in chapter 7 as well. The Runge-Kutta method is a name that I know that you guys have seen when we go and look, for example, over here at our numerical grapher over here. When we click open this box, and I know that you guys can't see it right now, but when I click this thing, it's opening up a drop-down menu that I know that you guys have seen, and I know that you've seen that there are in fact 3 different Runge-Kutta methods that are listed as options that I'm hovering over right now. You just can't see them on the video right now. But we're going to come up with what are these different techniques, how do they compare to one another, all that kind of good stuff to produce these graphs. So that'll be some stuff that we're looking at in the next coming weeks here with a little bit of our Python programming things here. After that, we'll be done with chapter 2. We'll be done with our numerical unit. And so after our programming topics is when we're going to start section 3.1. And that'll be really our look into saying like, okay, if we really want to solve these systems, what's our more broad strategy for understanding how we should go? What's our approach for those things? What I also kind of want to say here, well, I guess I should start from the beginning right here. I really appreciate this quote that I read in the textbook here. Finding formulas for a solution of a system can range from difficult to impossible. And I think that it's good that they're being honest like that because these are hard. We're not going, in general, we can't just solve all systems. There's only going to even be special cases of systems that we can solve even once we get into chapter 3, aside from the special systems for today. And so the point to this is that you could either think to yourself, well, if we can solve so few of these, what's it even matter if we figure out the handful that we can? That's one perspective you could take. Another perspective you could take is saying, since there's so few that we can solve, it really matters that we can solve those particular ones and understand their solutions. That's really, I think, a better approach for us to take on this because kind of what this is going to do is it's going to give us a framework to think about our more difficult systems that we aren't able to solve to say, well, I know it should have behaviors A, B, and C based on what we studied with our slightly simpler systems here, but it might have this other action based on these other components that are in the differential equation or something like that, right? So these are sort of giving us something firm we can grab onto so that once we're out in the deep blue sea of differential equations, we can say, listen, I at least know these couple core components right here, and I can relate my difficult scenarios to these core things that I actually do understand. Everything we'll learn out there in chapter 3. So few differential equations, particularly systems, are truly solvable. It really matters that we truly understand the ones that are solvable, and that's what we're hitting today and all of chapter 3. So in chapter 3, we're not just covering we're not just covering systems of differential equations broadly, but we are covering linear systems of differential equations. When I say linear, what I mean is they are of this general form where we have a linear x term and a linear y term in each of our differential equations for the, I don't know why I wrote those kind of out of order right there, dx dt and dy dt right there. It doesn't really matter. But in general, we're going to be focusing significantly in chapter 3 on these four coefficients, A, B, C, D, that we're looking at right there. How much x stuff, how much y stuff is in each of our linear differential equations. So these are really going to be the big focus of chapter 3, not systems in general, linear systems of x and y. Today, we're going to look at 3 special cases that we can already handle associated with these systems without learning any new techniques. 2 of our special cases are going to be directly tied to systems. 1 of our special cases is in fact going to be tied to second order differential equations rather than a system. What we did learn in our previous videos is that we can convert second order differential equations into systems of first order differential equations with a substitution. We will do that. We're going to end up seeing that the second order guy that we're going to look at today, we won't be able to handle its system version, but we will be able to handle its second order version. So that'll be our third special case today, is really a little bit more about second orders than about systems. But a thing that we saw in the last 2 videos that we're going to continue to emphasize is that second order differential equations are closely tied to systems of linear differential equations because we can always find a substitution to convert from one format to the other there. So our solving techniques should end up sort of having some underlying relation to one another. It's not until section 3, it's 3.5 or 3.6 or 3.7, where in our systems chapter, we'll cover second orders and we'll see exactly what that like underlying connection is going to be out there in chapter 3. So what are we doing here today? Well, what we want to do is we want to classify all of our linear systems into 3 different classifications here and talk about which ones can we do, which ones can't we do here. So let's identify these. So we're looking to say that this is our kind of general case up here, and I want to classify some special scenarios out of our general case right here. So here's the deal. The reason why solving systems gets to be hard is because our dx dt equation has y in it, and our dy dt equation has x in it also, right? So they are interrelated with each other, or we'll come to call them coupled. They've got that interrelationship where the rate of change of x depends both on x and y. The rate of change of y depends on both x and y. So I'm actually going to write our first one over here first, which is our really just our general format right here. Ax plus by and dy dt equals cx plus dy. And what I'm really saying here is A, B, C, and D are all not equal to 0, saying we've got all the parts that are in there, or at least one of our, or excuse me, no, both equations have both the x and y components. Oops, I got to slide over a little bit here, don't I? There we go. In fact, can I instead do this? That'll be a little bit better. I'll extend this back over a little bit. There we go. Cool. So this is our fully coupled case. And when we say coupled, we mean both differential equations involve both variables. Now, what would be the easiest possible case for us to handle here? Well, the whole reason why dx dt is hard to talk about is because it has y in it. So the easier case right here is, well, if there's no y, b is equal to 0. So one thing that might be really nice for a system is to have dx dt just include our ax terms, right? For this to just be a function of x. And for our dy dt to also, this should be a dy, I guess, if I'm following my lettering format up there, to just be a g of y equation right there. In our fully decoupled case, we're saying it's still a system of differential equations, but the x equation only has x in it and the y equation only has y in it. We've fully separated out the 2 dependent variables of interest from one another. So this is going to be pretty direct because in this case right here, we can solve the dx dt equation having no relationship to the dy dt equation and vice versa right here. That'll be good. So what's halfway in between? Well, what's halfway in between is where we get a little bit of mix of the decoupled and the fully coupled right here. So I guess the 2 different possibilities here are to have dx dt being our ax plus by, and then our dy dt though, so partially coupled meaning x involves both variables, but y doesn't. Alternatively, the other possibility here would be that our x equation, dx dt, has only x in it, but maybe our dy dt equation is the one that's mixed. It has both components, cx plus dy right here. So in this case, I have one easy equation to solve in our first grouping, the y equation, our second grouping, the x equation, and then one that has some interrelationship between the parts. So what we want to do today is today we are going to look at the decoupled and the partially coupled. We are not going to look at the fully coupled today. This is all of chapter 3 right here. So two of our special cases are the decoupled cases for linear systems and the partially coupled case for linear systems. These are two of our three special cases for today. Our third special case is in fact going to be a second order differential equation rather than a system here. So fully coupled case is essentially all chapter 3. We can handle the decoupled and the partially coupled cases already, so let's go ahead and check them out. The cool thing here is not just going to be our ability to actually solve the differential equation, but a little bit more of the analysis that we can do sort of intuitively from the information that we have. So for our first example here, let's go ahead and look at this system. It is a linear system because it has linear components of x and y only. This is fully decoupled because the dx dt equation only depends on x and the dy dt equation only depends on y. So what I think we should try to do here is find the general solution, infer the shape of the solution curves in the phase plane. I want to straight up know what all of the curves look like in the phase plane, which is a pretty tall order right there, allegedly, potentially. And then let's at least plot the one that's associated with 0, 0, and kind of make some general statements about what made it easy and will that always work out for us here. So some things that I'm seeing are this, and I should say there's some other things I want to talk about before we do this also, which is where might our equilibria be, right? If we said dx dt and dy dt equal to 0, the only possible way that this is going to happen is if both x is 0 and y is 0. Right? So it looks like that's an equilibria there. So I guess sorry, I'm gonna change this right here. Let's because the initial condition at 0, 0 just stays at 0, 0. I guess what I want to say is identify and classify the equilibria. So I'm finding that there is an equilibria at 0, 0, and I'm wondering if we know how to classify this. I am hoping that you're saying, well, I don't know how to classify this because what we've been seeing is with systems, it seems like there's some less typical classifications than what we saw in our first order, or our single ordinary differential equation setting, right? In chapter 1, all we saw was sink, source, and node, but we see some weirder behavior than that we've seen so far in our system, so we should be a little bit weary about this. But what I am seeing is that this x equation is decaying over time, right? If your x value is positive, then your dx dt is negative, so it's going to decay towards 0. On the other hand, if your x value is negative, then dx dt is positive because negative of negative makes a positive. And so if you're negative, you're going to grow towards 0. And as x gets closer to 0, dx dt gets closer to 0. So it's kind of honing in and slowing down in the x direction. The same exact thing is happening in the y direction, where things seem to be decaying towards 0 in the y direction. So I'm going to say here seems to be a sink. It seems like any initial condition for x and y should decay towards 0. So let's go ahead and see what we can do to solve these guys. So the good news is that the dx dt equation deals only with x. So it seems like this is easily separable here. Dx dt equals negative x. That means that we're going to get a 1 over x. Dx equals, I guess, negative 1 dt. We're integrating on both sides. And I'm seeing here natural log of x equals negative t plus c. And taking the base of e on both sides is going to lead me to x equals e to the negative t. And we certainly get like our little coefficient right there of a. Now, I guess what I want to actually slightly modify for what I just wrote right there, I'm going to rewrite this a little bit right here. I want to do two things here. That a is risky to me in the sense that I'm going to get something like an a term for the dy dt equation also, but they're not necessarily the same. So it's time for us to start making a distinction between our integration constants that we're getting out of each different equation right here. So here's the two small differences I want to make. One, I want us to really remember that this x is an equation of t, so I'm going to write this as x of t. And here I'm going to write this as k1 e to the negative t. So that k1 is like our a, which is e to the c, right? So there's our one of our solutions right there, one component of our solution. And hopefully you're seeing that we're going to get this essentially exact same action here for dy dt. So it looks like this is going to be 1 over y, equal sign too soon, 1 over y dy equals negative 4 dt. We're going to integrate both sides. I'm going to get my natural log of y equals negative 4t plus c. We're going to exponentiate with base of e on both sides. And what are we left with? We're left with y as a function of t. I don't know what I thought I was going to get all this in and no space for right there. Let's get this guy out of there. I need to draw a picture here still too. And what are we getting? It looks like I'm getting this e to the c. That's a constant to a constant. So I could call that a, but I don't want to get any confusion. I could call it k. I don't want any confusion. I'm going to call this k2 e to the negative 4t right there. So here's the thing that I'm seeing right here. And okay, here's I guess what I want to do. I'm going to take a look at some initial conditions that are a little bit simpler right here to help me see what my K1 and K2 values might look like. And basically what I'm saying is what are the, like, let's just pick some really easy values essentially for K1 and K2 to make this as easy as possible. And so I'm thinking we can look at some initial conditions like x of 0, y of 0 equals 1, 1. So this is saying when t is 0, x should be 1. When y is 0, y should be 1. If I do that, what I'm going to get here is x of 0 equals 1 equals k1 e to the 0, and therefore 1 is k1. And if I do y of 0 equals 1, that's k2 e to the negative 4 times 0. Well, that's again just 1, so we're going to get 1 for k2. And this would then lead me to my general solution that I might write in our vector form, x of t, y of t equals, and it looks like x of t then would just be e to the negative t, y of t would be e to the negative 4t. Right? And so what I want to ask is, how do I know what the graphs of our solution curves look like? Well, my question to you is, do you see some nice relationship between x and y? We want to graph this stuff in the xy plane. Do we see a nice relationship between x and y? It looks like you could just take the fourth power of x and you would get y. That's pretty cool right there. And notice, if we ended up with any other initial conditions out here other than like 1, 1, so the curve passing through 1, 1 should look exactly like y equals x to the fourth. If I had picked any less nice initial conditions, then we still would have gotten some fourth power relationship. There just would have been some other constant multiple. And this is good because I know exactly what the graph of y equals x to the fourth looks like. Even more than that, because we know that when we are graphing parametric curves, they aren't just curves, they're curves indicating a direction. Oh my gosh, I still need a little bit more room out here. So I'm thinking all curves look like some y equals ax to the fourth, with all trajectories decaying towards 0, 0. Right? We've already seen that both our x value and our y value should get smaller over time. We can see it with their solutions. We can see it with the differential equations right here. As time goes on, the value of x gets smaller and smaller and smaller, regardless of however large your initial condition k1 or k2 might have been. We've got negative exponentials. That's decaying exponentially fast, right? It turns out the speed of their decays are going to be related by a fourth power right here. We saw there was a direct algebraic relationship between the equation for x and the equation for y. Since we're trying to graph equations in the xy plane, we've sort of unparameterized this guy, is in a sense what we did. These are parametric equations for x and y. These are explicit equations relating x and y. In this case, we were able to do that unparameterization. So I am picturing for myself that I should be getting some like x to the fourth looking curves. Notice that x to the fourth doesn't quite look like a parabola. It's got sort of, it's a little bit boxier down there at the bottom here. This is like x to the 40th right here. It's like boxy down there. It's not, it's not quite a parabola, but it's certainly similar to parabolic shapes. And so I'm anticipating that we should be seeing these solution curves doing some decaying towards the equilibrium that we know is at the origin. And notice here that depending on whatever initial conditions we picked, it might be the case that this is going to be like a negative value for A. And so I am anticipating there should also be some other ones that are out here that might be like in the bottom half. But again, everything's decaying to 0. If you're negative, you're getting bigger. If you're positive, you're getting smaller, right? So I'm anticipating to get a graph that looks something like that guy right there, right? Let's go ahead and check technology and see if this graph agrees with what we're looking at right here. We've got the equation. We're going to go over to systems here. We've got dx dt equals negative x. We've got dy dt equals negative 4 times y. And oh man, ooh, that feels good. I want to make my curves a little bit smoother right here. Oh yeah, look at all these components that look like that fourth order type of stuff right there. I'll do my typical just click a whole mess of times out here. I wish these things went through both sides right there, but what we can see is we absolutely see all of our arrows are pointing directly towards the origin. We are saying that the shapes of all of the curves that we're generating are exactly the shapes of fourth order polynomials centered at the origin right there. So this is very satisfying that in this case there happened to be a nice algebraic relationship between our x and y solutions that allowed us to form an explicit y equals x equation in the phase plane. That's not always going to be possible. But in this case, it was right there because we were fully decoupled. I would also like to point out another nice thing right here. You should notice what's happening on the x-axis, that we have just exclusively straight line to the right motion. Notice that if your initial condition is on the x-axis, then you're starting at y equals 0. And if y is equal to 0, if y is equal to 0, if y is equal to 0, then dy dt is 0, so it never changes. So you should notice back here in our technology-based graph that our x-axis is truly the phase line for x. Equilibria at 0, sink towards it. Our phase line for y is exact, or our y-axis is exactly the phase line for y. The arrows are pointing vertically upwards and vertically downwards because for just the dy dt equation, we have an equilibria at y equals 0 and all solutions decay towards it. So again, notice that our x and our y-axis are literally phase lines, and we're able to determine all of the remaining solution curves in the phase space by identifying the algebraic relationship between our x and y solutions right here. So I hope that you find that as satisfying as I do, considering that is a pretty simple little case right there, right? This is as easy as a system's ever going to get for us right here, but still satisfying that we were able to kind of just do the algebra to determine where we're going to end up out there, graphically speaking, for all of our solutions. So let me go ahead and ruin my Microsoft Word document by bringing in this picture. All right, be my friend today. Yeah, it's not so hard, is it? I think it's fine if I add it afterwards. It doesn't like it when I add these pictures when I'm still trying to write some stuff here. So there we go. Satisfying picture that agrees with our graph right here. So that gets the check mark here. So nice and easy, fully decoupled. If your dx dt equation only has x and your dy dt equation only has y, then you're just doing two straightforward differential equations. You can handle these completely separate from each other, hence the name decoupled. They're completely independent of one another how we go to solve them. Now when we go into our second scenario here, our partially decoupled setting, in this case, one of our differential equations only depends on its own dependent variable of y, but the other equation is going to take slightly more work for us here. But let's kind of do the same types of things right here. Again, I want to identify real quickly that as far as equilibrium goes, only xy equals 0, 0 seems to be the only way. Y has to be 0 for dy dt to be 0. If y is 0, then x also has to be 0 for dx dt to be equal to 0. So there's only possibly one equilibria here. Only possibly. The only possible, excuse me, there is one equilibria. It's at 0, 0. There are no other possibilities. Man, I'm struggling to force that word possible in there right there. So let's go ahead and do this. So what I want to identify here is that one of these equations is hard. One of these is easy. So my step one right here is going to be to say, so I'm gonna label some step numbers here. dy dt equals negative 4y. I can handle this. In fact, this is literally the same dy dt that we had a moment ago. I think I can straight up say that this is separable. Y of t equals k, we'll call this k1 e to the negative 4t right there, right? There's nothing special to say about that right there. I'm asking you, what's the function y of t where when you take the derivative, you get back y times negative 4? You know that that's an exponential. You've done enough calculus, you've taken enough derivatives. Nobody's surprised by that. If you want to do the math, it's the simplest separable differential equation that we have. This is like the literal first thing we solved in this class was this guy right here. All right. So step one, we do the easy equation first. The point is that I now know an equation that is what y is equal to. So now what I'm going to do is I'm going to go plop this y equation into my dx dt equation here. All right. So it looks like what we're really getting here is dx dt is 2x plus 3 times k1 e to the negative 4t. All right. Now, the good news about this is that now this only depends on x and t. The bad news is it looks like we actually have some t stuff in here, so it seems like we're going to have to actually like do some math to figure this guy out. And I would ask you, how would you classify this differential equation? What name have we given to differential equations that look like this? You should notice that this is not autonomous anymore because it's got a t in it, but this is linear in x, right? This is a linear x term here with a dx dt. So let's go ahead and use our integrating factor to make this guy happen. So I want to solve this guy for x. So let's go ahead and do our usual moves here. dx dt minus 2x equals 3k1 e to the negative 4t. Now, one thing I've been kind of like yelling at you guys about is that these constants are really just like a basket, right? What we want to be a little bit careful about is once we have multiple constants, K1 and K2, they're going to have a relationship to one another. And so in these cases, I don't necessarily always go just like absorbing all of these constants in here. I think that we probably kind of could get away with that a little bit right here. But I'm going to go ahead and just leave that as a 3K1 right there. So our integrating factor here says to us that we should be getting a e, excuse me, let me write this as a mu. Our integrating factor is e to the integral of negative 2 dt, right? That's what we're looking for that, or the coefficient on the x term. So it looks like it's an e to the negative 2t. Looks like it's going to be our integrating factor here. So let's go ahead and multiply everything by our integrating factor. Notice here I'm multiplying by e to the negative 2t. I already have e to the negative 4t. So now we've got e to the negative 6t on the right over here. Over here, I'm recognizing that this on the left-hand side, again, this looks like my, you know what I should have done? I'm going to rewrite my ordering right here so that this looks exactly like I want this to look. I'm just changing my ordering right here. This is a minus 2 e to the negative 2t x, right? I'm jamming the e to the negative 2t in there because I know that this and this is now going to be my product rule, right? I've got the x left alone on one side, the derivative of x on the other. I've got e to the negative 2t left alone here, and the derivative of e to the negative 2t here. So it looks like this is really just the derivative with respect to t of x e to the negative 2t. I'm undoing my product rule here. And now we can go ahead and integrate on both sides to solve for x. So x e to the negative 2t is the integral, and it looks like I'll just write it here anyway. 3k1 e to the negative 6t dt. This is going to pop out for me a negative 1/6. So negative 1/6 e to the negative 6t plus, and I'll call that a c for right now. We'll make it a k in a second here. And so what do we got? We've got x e to the negative 2t equals 3 over negative 1/6 is negative 1/2. So negative 1/2 k1 e to the negative 6t plus c. And we solve by multiplying by e to the positive 2t to cancel the e to the negative 2t that we have over here. So it looks like my final equation for x of t, again, multiplying by e to the positive 2t to cancel the e to the negative 2t is going to give me negative 1/2 k1 e to the negative 4t plus, see, I want to write my k right here, right? And it doesn't really matter, I guess, that c is fine. C e to the positive 2t, right? We multiplied by an e to the positive 2t that was out there. So it looks like I've got my general equation for x. I know my general equation for y was our k1 e to the negative 4t, right? So it looks like I now have my solution to our system. Right? I've found the equations x of t and y of t that make the entire, just get out of here. Gosh, I got hopeful about how much room these things were going to take. So here's my overall solution right here. Right? And we can see what these steps were, right? We're solving the fully decoupled equation first. Then we're substituting that solution into our coupled equation. And then in this case right here, it seems like this should always end up being linear because the x term is, because I'm saying to you, we're only solving our linear systems right now anyway. And so there's always just going to be that linear 2x term. Whatever the 3y term ends up being over here, that's always just going to be your leftover stuff on the right that we're integrating, right? So the point is here, the x component's always going to be linear. So for our partially decoupled linear systems, you will always solve the decoupled part first, sub it into the partially coupled or the fully coupled part second. It will always be an integrating factor that you're looking to use for your solving technique right here. And it does look like we landed at a final system right here. So now let's go ahead and hit this thing with some initial conditions and see if we can play the same game as before. I kind of want to do two different sets of initial conditions here. So I'm proposing this is a set of initial conditions, but we'll also look at another set here and see some nice and some not so nice things. So I'm going to say here, I'm going to, it's mad at me right now. Come back to me. We're okay. We're all okay, Microsoft Word. Here we go. So let's look at one set of initial conditions that could be associated with this that are nice, and then we'll look at one set that work out a little bit less nice here. So what were these? We said xy being negative 1/2, 1 as my initial conditions. All right, so let's go ahead and apply these to our system right here. Immediately, I am noticing it is definitely easier for me to solve, let me just say over here. Whatever. It doesn't matter what variables you pick right there. I should have probably, for consistency's sake, done K1, K2. Doesn't matter. Our goal is to solve for K1 and for C based on these initial conditions. And again, clearly it is easier to solve for K1 first than it is to go into this guy. So the first thing I'm going to do is I'm going to solve this part right here. And I'm going to say y of 0 equals 1 is K1 e to the 0. And so it looks like we're going to get K1 is 1. Now I'm going to say x of 0 equals negative 1/2. That should be, what do we got here? Negative 1/2. There's the 1 from K1. We just solved for K1 and got it to be 1, so I'm plugging that 1 in. We're going to get e to the 0, which is 1, plus c e to the 0. So it looks like I'm getting here negative 1/2 equals negative 1/2 plus c. And so it looks like we're getting c is equal to 0. So that's what was so nice about this first set of initial conditions right here, is it looks like this is leading us to the final solutions. This is our general solution. So this should be representative of all the curves in the plane. If we're looking particularly for the curve that goes through negative 1/2, 1 in the xy plane, it's going to be this guy right here. So x of t, we've identified that k1 is 1. We've identified that c is 0. So it looks like we're just getting negative 1/2 e to the negative 4t. It looks like we're getting y of t. We solved for k1 to be 1. So we're just getting e to the negative 4t right there. So now I'm asking you, what should this solution look like? What does the solution look like that passes through negative 1/2, 1? What does that look like? Well, do you see some nice algebraic relationship between x and y? It looks to me like if you were to multiply x by negative 2, you would just get y. Oh my goodness, we just found that there should be a straight line solution in our solution in our phase diagram that's out there, at our phase portrait. Even though the x of t and y of t equations are both individually exponential functions, that exponential function is really just describing the rate of change of our solutions. It's saying they're decaying exponentially as opposed to quadratically or linearly. That's sort of like a speed conversation right there. The important thing is that the ratio of x change to y change is a linear change. And so it seems to me if we start anywhere on the line uh, that is associated with that is associated with get here and is associated with this negative 1/2 1 and goes through the origin, then all of those should be landing on one straight line looking trajectory out there, right? So I think we can say in general, any initial condition of the form negative a over 2 comma a will be on this straight line. Further, what's going to happen to those solutions? Well, it seems like they're both going to decay to zero over time. I can see these negative exponents on both the x and y solution. So, what have I found? What I have found is that there should be the line y equals negative 2x, so a slope of negative 2, should be a straight line solution in our phase plane. And it seems like, relative to the equilibria at the origin, that our solutions should decay towards that. And I know that that's the case because I know that no matter what x and y start at on this line, they are going to be the x value and the y value are going to decay over time. We've got those negative exponentials right there, right? So I know a straight line solution in the plane, and I want you guys to really remember, we really, really, really like straight line solutions because straight line solutions are guaranteed to sort of chop our entire phase plane in half. What this says to me now is I know that any initial condition that starts to the right of this line will remain to the right of this line forever, and any that starts to the left will remain to the left based on our existence and uniqueness of solutions, based on the fact that these are differentiable, or excuse me, that they're continuous, that our differential equations are continuous, and their first derivatives are continuous as well, their partial derivatives. So this is really nice. And now I'm going to point out something even nicer than this. Let's scroll back up and revisit our previous example. One of the things I yelled at you about right here is saying, oh, hey, look at your x and y axes and notice that these are just the phase lines associated with the individual differential equations. That we should have seen things that were decaying directly towards the origin on the x-axis and decaying directly towards the origin on the y-axis. And we knew that this was going to happen because if we just looked at each of these individual differential equations alone, that they represented, if you just look at dx dt, it's got equilibria at x equals 0, and all other solutions are pointing towards it. So that phase line is the x-axis. That phase line is the y-axis. Same exact conversation for dy dt. So my question to you is, do we have any of that going on down here? Well, what I can see is the x changes aren't going to be like that. But what I am seeing is it seems like if y is 0, then there's no change in y. So if we are on the x-axis, then the y values will never change. We'll stay on the x-axis for all time. And what type of action do we experience on the x-axis? Oh, an exponential decay is what we should experience on the x-axis. So it seems to me like, so we can also see if y equals 0, dy dt equals 0, and that should be giving us that piece of phase line right there, right? If the y value is 0, the x-axis, then the y value will never change. It'll always be 0. So we're only obeying x's change in information. And if we look at our original differential equation, if y is 0, then it looks to me like we should be having dx dt being a positive 2x right here. So it seems like we should be growing out of the origin right here. And so I actually drew my phase line backwards for this guy. So let me draw that again. That's what I really wanted to say right there. These two pieces of information collectively tell me that we should be growing away from 0 right there on the x-axis, right? If y is 0, we're looking at the x-axis. If y is 0, dy dt is 0, and dx dt is positive 2x, saying grow away from that equilibria at 0 that's right there. So I think that I actually know two straight line solutions that live in the plane. And again, this is just awesome. Straight lines are really the only shape that's sort of guaranteed to chop the plane in half, basically. So we can now see that there are 4 quadrants in which our solutions are guaranteed to all live. If you, and I say quadrants sort of loosely right here, but again, if you start in this upper right region up here, you're going to stay in the upper right region for all time. It's got to be the case. We can't cross over these straight line solutions. So having 2 straight line solutions right? So again, anything that starts in any one of these regions as defined by these 2 straight line solutions that we found will stay in that region for all time. So what I am picturing for myself now for some additional solution curves that I believe must be in the plane, for example, is what's going to happen if we start at that initial condition right there? Well, it seems like I'm guessing my solutions are going to vaguely do what the nearby solution says that it's going to do, right? It's not necessarily, I don't expect this to be a straight line solution here. I think that if there were more special straight lines, we would have found them. Or there would be something indicating that this is like only straight line solutions. I'm not seeing only straight line solutions, right? I'm seeing that there could very easily potentially be some curvature. The only reason we got that straight line solution was because c was equal to 0. So the e to the 2t term wasn't in there. We only had the 2e to the negative 4t's giving that linear relationship. That was special to c being 0. If ever c is not equal to 0, which should probably be most of the scenarios out there, we would have this extra term, which would make us have curvy solutions rather than straight line solutions. But again, I'm picturing that this solution is going to imitate the nearby behavior of other solutions. And what that seems to suggest to me is some sort of like something like this, right? Similarly over here, if I started right here, it seems like I should do what the nearby stuff is doing. But once I've decayed a bit following in this solution that I was nearby to, now I'm a little bit closer to this one, which is pushing me back out. So I'm kind of anticipating some stuff that's going to move, again, sort of following those trends that are out there. So kind of my anticipation is that I'm going to see some curves that are, again, they're imitating the nearby solution curves out here. So it seems like what I'm anticipating seeing here is some action where any initial condition that starts to the right of our diagonal line, I think it's going to end up going off towards x equals positive infinity and y tending towards 0. I think that if any solution starts to the left of our skew line, it's going to head off towards x equals negative infinity. And again, this y value seems to be decaying towards 0 right here. And why is the y decaying towards 0? I'm watching it happen right here. There's y decaying towards 0. I can see it at the top of the screen. So let me generalize this, and then we'll go and do this one using technology here. So let's make some general statements here. So if we have initial conditions where our y value is greater than 2x and our y value is greater than 0, then it looks like we're going to have our x value. So here I'm saying y is greater than 2x, meaning we're above the skew curve. We're to the right of that skew curve, that oblique line right there, the angled line. Y greater than 0 means we're on the top half of it. So this is sort of like quadrant 1 sort of stuff right here. What's going to happen? I think that my solution curves are all going to get pushed out to the right forever. And I can see that even as they move farther away, I still think they'll be lightly influenced by this downward motion right here. So I think they're going to sort of asymptotically approach the x-axis basically. So this should be saying to me, x is going to go to positive infinity and y is going to go to 0, but it's going to do it from above. So I'll give it the little plus 0. Y is going to approach 0 from above, right? Let's make some more statements that look like that. We could have also, so this is sort of like our Q1 right there. On the other hand, we could be still to the right or above that oblique line, but we could be on the bottom half where y is less than 0, right? So this is sort of like our Q4, right? Approximately the fourth quadrant stuff over here. Right? Again, it seems like any initial condition that starts there is going to get spit out to the right in the long term. So our x value is going to go to positive infinity. And our y value is also going to approach 0, but it's doing it from below. So it's approaching 0 from below. So the y's are always going to be negative because they started negative and they're decaying towards 0. On the other hand, we could have our y values being less than 2x, but above. All right, this is sort of like our Q2 scenario right here. And again, it's not quite the second quadrant, but it's pretty close, right? It's this region that we're looking at up here. And it looks to me like all of these trajectories should end up having the x value go to negative infinity, a y value going to 0 from above. And finally, if we start in that third quadrant where both of these things are going to be negative right here, then x should go to negative infinity, y is going to go to 0 from below, and that is sort of our Q3 scenario there. And again, keep on putting these in quotes because it's not truly those quadrants, but I think it's a pretty good descriptor of those guys right there. So this is what I'm saying when I'm saying we want to check out all these other initial conditions. Our issue is going to be is that, and I guess I want to do this right now. If I were to pick any other initial conditions that didn't fall in these straight lines, what we're going to find is we're just going to get some numbers that aren't 0 for both k and c. And when we do that, it's going to give us the parametric equations for these green curves that I've drawn that I don't quite really know what they are, right? Like if I just told you that like K1 is 4 and C is 6, can you draw the curve? I don't really think that the answer is yes, but I think that you're going to get one of the curves that looks like this. So we've done a lot of math that we're sort of assuming is right. Let's go ahead and check out our technology right here, see if technology agrees with this. So when we go over there, I want to do something that's really important, which is I'm not just going to click like a crazy person all over my graph. The first thing that I want to do is I want to manually input 4 initial conditions to represent the 4 branches of our 2 linear types of solution. The linear solution of y equals 0, the linear solution of y equals negative 2x right there. I want to manually input inputs that are going to give me those 4 straight lines first. Then I'm going to click just 4 times at first, and then I'll go crazy because I want to see if these curves are exactly what we should be anticipating here. So let's go ahead and do this. I want to remind myself what my original differential equation was. 2x plus 3y and negative 4y. 2x plus 3y and negative 4y. 2x plus 3y and negative 4y. Oh man, I cheated right there. Oh, I ruined it for myself. So let's go ahead and do this now. We know that we were looking for stuff that was on this line, this y equals negative 2x. So I think I could do something like, okay, just to make sure here's what I'm going to do. I'm going to do like negative 2 and 4. So notice that y equals negative 2 times x. Negative 2 times x does give me y. And it doesn't like that because it's above my thing right here. It didn't like that just because it's off the screen right there. And my max Y was only 3. So now let's do this. Oh man. Ooh, that feels good right there. Let's go ahead and switch our signs right here to get the bottom branch of it. Oh yeah. Oh, yeah, those straight line solutions. Oh man, do we like straight line solutions. Let's go ahead and check out our axes over here. We can also do things like negative 4, 0. That should be the left-hand side of the x-axis. And you can't even see it, I think, because it did it in black because it's a total jerk. Uh, and if we did positive 4, 0, then yeah. Oh, I see what's happening. Sorry. The reason why we're not seeing anything is because I started the initial conditions here and here, but they're actually getting pushed out, and so there was nothing for it to graph outwards from there. I think I want to be doing something like this. Let's go 0.10 right there. And hey, there we go. We see the orange one show up. And as you can see, it didn't graph the first 0.1 of it right there. Similarly, I can do the negative 0.1 right here. And there we go. There's our yellow one. So, you should be very happy about straight line solutions. They are going to be the thing we're going to hunt for in all of chapter 3. Unfortunately, we won't always be able to find them, but thinking about straight line solutions is going to be like our guidance for this. The other things I want to see are, do we get those solution curves following those proposed trajectories that I was suggesting to you? And it sure looks like we are right there. So hopefully you find this to be highly satisfying, that we're able to sort of intuit what the other curves are going to look like, even though we really don't know how to interpret those parametric curves. It seems like if we can find two linear solutions that weren't like the same thing, that should sort of guide us to fill in the entire phase plane. That's really, really powerful, right? So this is sort of one of the things that I want to burn into your brain for chapter 3, since we're going to sort of take 2 weeks to talk about programming before we get back into this, is straight line solutions are your best friend in these contexts right here. If you can come up with two straight line solutions, then you have essentially determined what all of the solutions look like in the entire plane out there. That is really cool. So let me click through a few more for our satisfaction here. But again, those straight lines, that's the good stuff right there. So I'm going to go ahead and snip this guy so I can throw it into the notes. And we now recognize the value of a couple of straight line solutions. Okay, so those are the two cases that we wanted to talk about for systems here today. The cases of the fully decoupled, as easy as it's going to get. The case of the partially decoupled, where we're going to have to do some work, but it's not too bad. Oh, sorry. Here we are. Our fully decoupled systems right here. X and Y fully independent of one another in their equations. Really, really easy. Our partially decoupled took a little bit of work right here. It should always result in you getting one that's basically free, one that's going to be an integrating factor. And that's what's going to happen every single time right there. You're always going to end up with solving a linear differential equation for your second solution right there. Getting our general solution with two unknown parameters. If I was being smart, I would have called them K1 and K2. Given any initial condition, we can identify what the curve looked like. Here, I presented to you these with some pre-knowledge from me, which really I mean from the textbook that said, hey, check it out. If you smartly pick this initial condition right here, it will make your one disagreeing term, the e to the positive 2t, go away, so that there are only very relatable terms left for your x and y equations right there, meaning you can interpret the relationship between x and y, identify it should have been a straight line, identify the other straight line from just looking at one of our two axes right there, since we were partially decoupled, recognizing that two straight line solutions allows us to infer all other solution curve shapes in the entire phase plane, allowing us to make general long-term behavior descriptions of any initial condition in the entire system, right? So this is huge. We just described the long-term behavior of literally any initial condition for the entire system by identifying only the two easiest solutions. That's awesome, right? So see this for what it is. A little bit of work, two solutions, gave us infinite solutions, general descriptors. We would still have to do some work if we wanted to get more specific calculations associated with all those things, but I know the general behavior of all of those things, right? One thing I want to say about this before we walk away is, how would you classify this equilibria at the origin right here? We know that there's an equilibria at the origin. We can see it happening in our diagram right here. But it's weird because it seems like along one of our straight line solutions, things move in, but along another one, they move out. So it seems to be doing this weird job of partial source, partial sink, but it doesn't seem to be like a node in the way that the sink source sharing was a node in our 1D systems here. So that one's another weird one, right? We're going to want to like be a little bit more careful with its classification. We will classify this equilibria out there in chapter 3, right? Cool. So that covers two of the three special cases that we want to consider today. For our third special case, we're not going to talk about systems. We're going to talk about a second order differential equation right there, not a system. And we want to see what's so special about these that we can actually handle these already. So here's what we're going to do. We're going to return to our mass on a spring. Man, I dropped a bunch of my words here. Mass on a spring, physical system, but we're going to make an important adjustment from before. Now we're going to actually include friction. The last time we talked about a mass on a spring, we neglected friction. We said, let's assume that this is on the world's iciest surface and that once you set it in motion, only the spring force acts on it to push it back and forth forever. Now we're going to say, no, there's actually friction in kind of anything that's ever touching a surface. Okay. In all practical systems, that is the case. And so let's include a friction term here, right? So where we went with this is we said that our, let's draw our diagram here. Here's our mass. Remember that we're measuring the displacement from rest, right? So we're thinking of this as like our x equals 0 location right there. If I was at x equals 5, that means I've stretched the spring by 5 units. If x is negative 5, then I have compressed the spring by 5 units right there. All right, what we know we want to kind of think about right here is we want to say that we've got Newton's second law. That's going to bring everything together. We've got Hooke's law. We've got our spring force. Now, this is important. We want to think about how springs work. What's the spring force going to do? Does the spring, the force that the spring applies to that mass, my question is, does it care if the mass is moving? And the answer is no. The amount of pulling or pushing that the spring is going to do to that mass is exclusively dependent on how far the mass is from rest. The important verbal description of a spring force is that a spring force is always resisting position. Spring force resists position. So the force for the spring, it resists negative position, x. The strength of the spring will be described by some spring force constant, k. Right? Resist is the negative, position is the x. We also have a friction force. And my question to you is, using the words that we just used, how's the friction force relating to this mass right here? What does the friction do? Does friction care if you are here or here? No. Friction is a force that is completely independent of location. Friction cares about velocity. If you are moving very quickly, then there's a lot of frictional force resisting your motion. If you are moving very slowly, then there's going to be a very small friction force. Friction is also a resistive force. It opposes motion. So when we talk about a friction force here, which by the way, I'm looking down here just at my notes, the letters that I'm using right here. A more general name for a friction force is a damping force. There's lots of different versions of damping that aren't just friction. If you are dropping something out of an airplane, you know that it's going to experience air resistance, right? That's a damping force right there because it is resisting your falling velocity right there. Eventually, the damping force of air resistance is equal to your acceleration due to gravity, and you just don't fall any faster. That's what we call terminal velocity. That's when the damping force is equal to the gravitational force. And the damping force, because it resists motion, gets larger and larger as you fall faster and faster, and it gets larger and larger until it is equal to and opposing that force due to gravity, so you don't fall any faster. That's why things reach a terminal velocity. So the thing I'm trying to bring up here is that that letter D is typically denoted for our damping force. In our case, we have the particular damping force of a friction force. There is no real wind resistance or air resistance that we're considering here, although very technically there should probably be a very small amount of air resistance here. We're neglecting that. We're saying friction force is certainly our largest damping force in this case right here. So this guy is going to have a similar structure right here, where it is a resistive force, so it gets a negative. It is going to be proportional to the friction of the coefficient of friction between the surfaces, right? We can imagine if this is an ice cube on ice, it's probably going to shoot by really quickly right here, as opposed to if this is like a rubber shoe on sandpaper, there's going to be a massive amount of friction, right? That's held in that coefficient B, just like the strength of a spring is held in the coefficient K. But notice that this is not resisting position, it's resisting motion. Motion, velocity, x prime, right? That's velocity, that's right there. So we can combine all of this stuff now into one nice second order differential equation. And as you can see, as we're tending towards the very bottom of the screen, is once we get the system, once we get the second order, we can convert it into a system the same way that we did before here. So what we want to do is we want to do our F equals ma. Our forces are the sum of the spring and the damping forces. Our motion is times acceleration, which we know is the second derivative of position. Right? Now we can write out the whole dang thing here, which is negative kx for the spring force, negative bx prime for the damping force, the friction force, equals mx double prime, our mass times acceleration. Let's just go ahead and rewrite this thing into a little bit nicer of a format here. I'm just going to add these two negative terms over to the other side and get a mx double prime plus bx prime plus kx equals 0. And it's pretty typical that we want to make some nicer coefficients for this. So this is me just screwing around with some constants here. Nothing fancy going on. I just want to write this in a little bit easier to manage format right here. We'll call those some new letters here. And this is our general form of a damped harmonic oscillator. That's pretty cool that we just built that from scratch right there. All we needed was Newton's second law, a description of a general spring force, and a description of a general friction force, and we now have the general form of a damped harmonic oscillator. So this is going to model exactly the behavior of this spring over time, depending on things like the amount of mass, the strength of the spring K, and the coefficient of friction, B, the amount of friction between the mass and the surface that it's sitting on right there. Very cool. Our question is, can we solve these guys? Can we just straight up do it without learning any new techniques? The thing that I'm thinking to myself is we've just had some success solving systems today so far, right? We've seen that we can handle these decoupled and these partially coupled systems. So let's go ahead and do our conversion into a system to see if we can just knock this guy out. So we say things like the derivative of position with respect to time, that's velocity. We're calling that our x prime right here, right? Then the derivative of velocity with respect to time, that's what we're calling, that's our second derivative of position. That's our acceleration, right? And so I'll call that a for right now, but maybe we want to kind of rewrite this a little bit as dx dt equals v, and then our dv dt should be our x double prime term. What is x double prime equal to in our equation? Well, subtracting these two terms back over, I'm going to get a negative qx minus p. Notice here, x prime, that's just v. So minus pv. Looks like we converted this into a system. So this is typically how general form of damped harmonic oscillators are given, but it looks like, and I don't want to ruin this, I'm giving away the surprise down there. It looks like this is our system. I don't know. System format of a damped harmonic oscillator. Okay, so the question is, can we handle this? Have the things that we've done today gotten us enough that we can just handle this thing? How would you classify this system? Is it coupled, partially coupled, or fully decoupled? It can't possibly be fully decoupled because I see x's and v's both occurring in our second differential equation. But it does look like we only have one term here, so it seems like we can think of this as being partially coupled, right? Well, no, because it looks like my dx dt equation depends on v and my dv equation depends on x right here. This is a fully coupled system because each differential equation depends on its opposite variable. I'm going to say it almost looks partially coupled. So the bottom line here is, yeah, this is going to take an actual smarter technique that we don't have yet, that we're going to get in chapter 3. But again, don't be misled by there being a single missing variable from dx dt. Even just the differential equation dx dt equals v, dv dt equals x, that would be fully coupled because there's v stuff in the x equation, there's x stuff in the v equation. They're fully mixed together in there in that sense. We don't have one differential equation that only depends on one of our dependent variables. So we can't say that we're partially coupled here. So this is a fully coupled system, so we can't handle this in its system form. But it turns out we can actually do the second order differential equation. So let's return to our x double prime plus px prime plus qx equals 0. And let's see if there's something special that we can do here with this guy. What I want to do is I just want to make some guesses. Could we just straight up guess what we might end up doing for some of these things right here? So here's the thing that I'm thinking to myself. The 0th, first, and second derivatives of x are all only apparently going to differ by a constant from one another because they all eventually need to cancel. So my question to you is, what families of functions are going to work? Well, here's the thing I'm thinking. Could a polynomial work for x of t? That's my first question to you. And here's what I'm thinking to myself. If I were to pick, for example, and I'm just throwing an example here, suppose that we picked x of t to be like a cubic function. If that were the case, then we would get q times a cubic, we'd get p times a quadratic, we'd get just a linear for x double prime here. Could that possibly be equal to 0? The answer is no. And that's because it could be that the squared term and that the linear term and that the constant term all cancel away, but there would be the cubic, the t cubed term that would come out of qx right there that would have nothing to partner up with to cancel away to 0 because we're taking derivatives of these other terms. So no, the highest order term couldn't cancel. So I'm seeing here there is no way that there is a polynomial solution to this because, again, think of x being a cubic in t. The t cubed term will be in here. This only has as much as a t squared. This only has as much as a t. So even if the squared stuff and the linear stuff and the constant stuff could cancel by mixing and matching with each other, there would be a t cubed coming out of this guy that guaranteed wouldn't have a partner to cancel with from the others. There's no way it could work out right there. Right? So could it be polynomial? The answer is I know for a fact it's not possible for there to be a polynomial solution to this guy. What else might we see? Now, another thing I know is that this thing seems like it's going to be doing some back and forthing behavior, and we've talked about this. When we saw our undamped oscillator, we saw that there actually was some trig solutions here. So I want to say to you, could this be trig? Well, the thing I'm seeing here is if we picked x to be a sine function or a cosine function of t, suppose that x was the sine function, give or take some constant multiples, like a sine function, right? Then the derivative would be cosine, and the second derivative would be back to sine stuff again. So it seems like our sine terms here and our sine terms here could potentially cancel because we'd get like positives and negatives, but that would introduce some cosine stuff here that wouldn't have any cancellation partners. So it doesn't seem like just sine would work. Right? And kind of for a similar reason. I'm saying I know that I need all three of the groups of terms to come together and cancel away to be 0. If I just picked sine of t or cosine of t, my q of x stuff could cancel with my x double prime stuff. That's what happened when we did our undamped oscillator. But now that we have this damping term in here, this would involve cosines, which wouldn't have any partners to cancel away with to get to 0. And that's the same for whether we pick sine or cosine. But you should notice that maybe we could do some like x of t equals some like, I don't know, like a sine t plus b cos t. In that case, we would get sines and cosines here, cosines and sines here, back to sines and cosines here. It seems possible to me that that's actually going to work out because we'd be getting some mixing and matching of sines and cosines from all three groups. As long as the p's and q's play nicely together and we pick the right x of t, that actually maybe would work right there, right? Now I'm saying to you, though, what's the other one? When I say to you the derivatives of a function only differ by a constant multiple, I'm hoping there's one really big thing that's jumping into your head, is that exponentials, it seems like some x of t being equal to some like e to the, now I don't want to reuse any letters that I've been using up here. I've used a's, b's, c's, d's, m's, p's, q's. Oh gosh. I don't think there's any letters left in the alphabet, is there? Now, let's think about what I just said right here before I move on. If I pick this to be e to the wt, then I could get some e to the wt stuff coming out of all three of these. It seems like in this case we would need p or q here to be negative. But does that really even make any sense? Not really, because p and q are guaranteed positive because they are a coefficient of friction divided by mass, and they are a spring force or spring coefficient divided by mass. So notice here that p and q are guaranteed positive, and so that's sort of an issue for me here. But I can kind of fix our issue by saying, well, if we were instead to make this an e to the like a negative term right here, then maybe that actually would work out, right? If that were a negative, then now when I take my derivatives, I am getting negatives from, or I'm getting positive stuff here. I'm getting negatives here, and I'm getting more positives here because two negatives have been popped down by the derivative, so we're back to positive again. Now it maybe seems like all that stuff could cancel. So I'm thinking this seems plausible to me and this seems plausible to me. So for our last thing for today, let's see if we can just guess our way to success. That's our goal here. I want to guess that that's going to work out for me right here. And what I'm going to do is I'm going to give myself a sample problem to do. Um, so there we go. There we go. So here's what I kind of want to say here. Mm. So I'm picking P and Q to be 5 and 6 just to give us some nice numbers to work with. Let's go ahead and hit this thing with our first guess right here. My point is with this guess is I'm saying I think there's something of this form that might work, but I don't know what W should be. So let's go ahead and see if we can solve for what W must be to make this guy work out here. So what I'm noticing is if I want this to work out, I need this equation to be true. So I need X, I need X prime, I need X double prime. So let's go ahead and find them here. So X prime of T should be negative w e to the negative wt, and x double prime of t is going to pop down another w, so I'm going to get positive w squared, because negative w times negative w is positive w squared, e to the negative wt. This is going to allow me to rewrite our differential equation x double prime plus 5x prime plus 6x equals 0 as e to the negative wt plus 5 times negative w e to the negative wt plus 6 times w squared e to the negative wt equals 0. What I'm noticing is that there's an e to the negative wt in all three terms, so let's go ahead and factor that guy out. What do we have left? Well, let's see here. It looks like I am seeing that we have a oh, wait a minute. I wrote that. I did this like backwards right there, didn't I? I did do this backwards. I was like, this doesn't make any sense. Sorry, I did this wrong right here. X double prime, that's my W squared e to the negative WT. I flipped for some reason my first and my last. That one is just straight up e to the negative WT. That was X, 6X. So that's 6 times e to the negative WT. E to the negative WT. Okay, now I fixed it. Now I've got, when I factor out my e to the negative WT, I'm seeing we have a w squared survives from the first term, minus 5w survives from the second term, plus 6 survives from the third term. Can you see some values of w that might make this true? Uh, uh, uh. So it seems to me like we are finding here that x of t equals e to the negative 2t would be a plausible solution for x. I just found that 2 works when we guess e to the negative wt is a solution. So e to the negative 2t should be a solution. Notice that we can now rewrite this in terms of our system solution, which we might have actually wanted, so we can think about a phase plane here. Our system involved dv dt. Well, dv dt is really easy since that's just the derivative of v, right? So the derivative of this guy should just be the derivative of x. Notice that in this case right here, v equals negative 2x. Right? That's one of our possible solutions. The other thing that we could see is it seems like x of t could have instead been e to the negative 3t. In this case, our v of t for our system, which by the way, I want the system because that's what gives me my x and my v axes when I think about my phase plane out there. So that's why even though we solved this by doing the second order differential equation, still think about my solutions in their system setting is helpful for me for visualizing the graphs. So it seems like we have found two general solutions out here, and because they had very nice relationships with one another, I think I know what our phase plane looks like here. I think that I've got my line of slope -3 as well as a line of slope -2. Furthermore, what I know is I'm thinking about this physical system. This is a spring, a mass on a spring that does experience a damping force. So what should eventually happen to this mass on a spring? How much position should it eventually have away from rest? How much velocity should it eventually have? Both those should be zero. I absolutely expect that over time my positions and my velocities are going to decay down to zero. So I am anticipating, aside from just knowing my straight line solutions, I'm pretty confident that they should be decaying towards zero. Because I'm just thinking about my physical system. This is a mass on a spring experiencing friction. It's got to eventually have no position and no velocity. Having that x equals zero being my general solution right there. Now, a little bit less clear what our overall solutions are going to look like right here. Sorry, that shouldn't be a t, that should be an x right here. But what these remaining ones are going to look like. But we're going to handle all that in detail out there in chapter 3. I feel pretty excellent that I was able to find two straight line solutions right here. So the last two things I want to do for the day are, let's go check this out using technology. And then let's think about what our last guess was with those sines and cosines, see if that would have been a possible route also, and then we'll call it a day here. So let's go pop over to technology. I've got my system here. Remember that we chose P to be 5, Q to be 6. I'm going to use that right here, or excuse me, right here. P to be 5, Q to be 6. All right. So it looks like we're going to get over here with our system that dx dt should be just y. That's v in our case right here. And then what I saw here is that this should really be like the system that looked like, now let me look back over real quick here. We're saying, and again, we're saying P is 5, Q is 6. So it should be negative 6x minus 5y. Negative 6x minus 5y. Negative 6x minus 5y. Negative 6x minus 5y. Again, what I'm picturing for myself is I would like to say, are there a couple straight line solutions out here that we're actually following? Where did we think that those were? We thought that those were located along the lines of y equals negative 2x and y equals negative 3x. So let's go ahead and plug in some initial conditions that should fall exactly on these straight lines to see if we actually get them or not. All right, so I can do something like if I make my x be negative 1, then my y should be positive 2. Ooh, nice straight line right there. If it's negative 1 and 3 should also work on my other line. Oh, baby. Oh, oof. That feels good. And then we should be able to instead go into the lower right ones as well. Oh, yeah. I might have to look at these graphs a little bit later on my own. Oh, gosh. Oh, that's some good looking straight line curves out there. Now, a little tougher for us to interpret the rest of the phase plane that's out there. Those might not quite have been the curves that you were kind of guessing right there. This is going to require a little bit more of our chapter 3 discussion for us to kind of convince ourselves that this is what the rest of the behavior should look like. And you should notice that this is a really weird shape. This feels to me like the remaining solutions are trying their hardest to be spirals, but they're getting blocked by a wall of some straight line solutions. It seems like these are wannabe spirals. Almost spirals, but to spiral you'd really need to do some circling around, and these just can't get over a wall. There's a wall that's preventing them from doing that looping around right there, but they feel like they want to spiral to me. We're going to look into that in depth out there in chapter 3, all right? But hopefully you feel pretty dang good about these straight line solutions that we found. Again, being very helpful guiding solutions for us when we go to try and do some of this interpretation by hand here. So our last thing is I just want to say, what about those sines and cosines? Is that going to work for us? Let's go find out. Oh man, oh, be my friend, Microsoft Word. Just a few more minutes. Um, so let's say here, what about that other guy? What if we tried? Something like, I don't know, what I suggest for myself right here? A sine t plus b cos t. Well, if I did this, then I'd get x prime equals a cos t minus b sine t. I would get x double prime is going to be negative a sine t minus b cosine t. Let's go ahead and throw this into our x double prime plus 5x prime plus 6x and see what we end up getting here. If I do this, so this one's going to take a little bit more room for us to write out right here. I should be getting a negative a sine t minus b cosine t. That's my x double prime plus 5 copies of a cosine t minus b sine t. And then we get 6 copies of x, which is just the a sine t plus b cosine t. All right. Sorry. I forgot to do my flipping over right here. Here we are. So we're going to make our other guess here. What if we chose x of t to be a sine t plus b cosine t? I determined my other two derivatives relative to our differential equation. I want to throw those guys in there. There's our x double prime. There's our x single prime. There's our regular old x right there. And my question is, can we determine are there a's and b's that make this true? So I want to kind of blow this up a little bit. And let's go ahead and group up some common factors here. Things like, how much sine of t do we have? Well, I have negative a of it here. I have plus 5a of it here. Oh, wait, sorry, that was wrong. Okay, sorry, do that again. I have negative a sine stuff here. I have negative 5b sine right there. And I have plus 6a sine there. What about my cosine stuff? How much cosine do I have in total? I've got negative b of it here. I've got 5a of it here. And I've got 6b of it here. Now, the thing that I'm noticing is that on the right-hand side of my equals sign, how much sine and cosine do I have is 0. I don't have any of it, right? So it looks like this is going to be something that says, I'm going to combine some like terms here. This should be saying to me 5a minus 5b should be equal to 0 because I need to match up the amount of sine stuff on the left with the amount of sine stuff on the right. Oh my gosh, how many times am I going to write the wrong thing right there? Write the number 5 so we can wrap this up, Tony. Minus 5b. And this should be equal to 0 because there's no sign on the left. How much cosine, there's no sign on the right. How much cosine is on the right? Also 0. So I'm noticing here that we should be getting 5a plus 5b is equal to 0 here. Oh, look, it's a system of equations that we can solve. Uh-oh. So here's my issue with this guy is it looks like I guessed my a sine of t, b cosine of t to be zero or to be my solution. But when I found what values of a and b make this work, all I found was that a and b both need to be zero, giving me x equals zero. And so notice, is x equals zero a solution to my original differential equation? And the answer is trivially yes. Trivially, if you make x zero, then everything goes to zero and we get zero. That is our lamest possible solution that we could end up with right here. Also notice up in our system form, if x is zero, and if we're looking for like equilibria, then it needs to be the case that v is equal to zero right here. Like we ended up in sort of our trivial solution. Um, so this is basically saying no. It doesn't look like we're going to get any good general solution of the form x of t equals a sine t plus b cos t, right? If there were, we would have identified coefficients a and b that made it happen, and we found the only coefficients on sine and cosine that would make it happen is both zero, meaning no sine and cosine contributions. Now, the reason why that's happening is that damping term ruined the whole dang thing for us, right? We're not just going to get periodic solutions. We should be getting decaying solutions over time. And so this guaranteed persistence of that, the periodic function is kind of what ruined that for us. So our conclusion for this little lesson right here is you should be kind of satisfied that we did this, but it kind of sucks because we just did this by guess and check. We said, I don't know, are there solutions that look like this? I don't know. Let's just plug them in and see if we can find coefficients that'll make the differential equation true. We managed to do it. It did lead us to some straight line solutions that we're going to identify in much greater length out there in chapter 3. So it's like good because we did it. But it's bad because like should guess and check really be our primary technique for solving second order differential equations? And the answer is, we kind of want to do less than that, but or better than that, I should say. But also you should be noticing, it seems like there is a pretty direct correlation between constant coefficient second order differential equations and solutions to quadratics. It seems like that relationship's going to be there regardless of what we chose for P and Q. And maybe we could factor them or maybe we couldn't. Well, what happens when you can't factor a quadratic? You got to go to the quadratic formula. What occasionally happens when you go to the quadratic formula? Well, maybe there's zero, maybe there's one, maybe there's two solutions. We got two real solutions here. Seems like there's maybe a whole bunch of quadratic scenarios that we might want to consider that might lead us to different behavior over here. All right. So that's all the stuff that we're going to sort of work towards in our future chapter 3 content that's out here. So we can handle our fully decoupled systems. We can handle our partially decoupled systems with an integrating factor. We can handle sort of our constant coefficient second order differential equations as long as they're equal to zero by making a guess of an exponential and identifying what coefficients on the exponential term will make it work out. We should expect that sometimes there's two solutions here, two real solutions, but maybe there's only one real solution. Or maybe one of the real solutions is zero, which would make this look a little bit weird. Or maybe we get repeated solutions, which then we'd only get one straight line. Or maybe we're going to get complex solutions, and what does that even mean? Do we even care about those? Great. I'm glad that you're wondering all the same things that I'm wondering because those 4 questions are sections 3.2, 3.3, 3.4, and 3.5 coming up in chapter 3 out there. We're going to be looking quite a bit at these guys right here. So this is all I've got here for our 3.2 stuff for our special cases for systems. Our next video, we're going to start with our programming topics. And so for our next video, I'm only going to be essentially writing some code, and you guys are going to imitate all that code. And for your homework, you're going to be submitting some programming solutions to me that you've produced out there. RGPT, I've got to wrap this one up right now because I've got to make another video here in a few minutes for my trigonometry class, but we can certainly do some other office hours related things in office hours on Monday, Tuesday, and Wednesday. So I will see you guys for some Python programming in our next video. I am super duper excited. This is sort of like my little favorite part of the class right here. And that'll be essentially 1.4. So you guys should read your section 1.4 before the next video, and we'll essentially do 1.4, but also learn a bunch of our programming things out there. That's all for me for this video. Have a good one, everybody.